Thank you. That's me. Yeah, that's good. So let's see how this works. That's fine. Okay. So my name is Joe Goodbread. I'm CTO of Rheonics. We're here as initially as a sensor company. We provide sensors for measuring density and viscosity of slurries with an in-tank system. And after I completed this presentation, laying it out and all that, I looked back at the theme of the conference, and I realized that it's about people, skills, and knowledge, not necessarily directly about the technology. And it made me realize that this is one of the things that is most important in the investment casting industry, which is how to take, let me go here, so that's the introduction, that's less interesting, how to make the empirical and subjective knowledge of the current generation of investment casters, how to make that available to new people in the coming generation. And that's a really interesting challenge for the sensors business. Why? Because we thought we were just trying to measure slurry properties, viscosity and density, but we're actually trying to capture the consistency of slurry. And that is different from just the numbers that you can put on those two properties. And we consider that up to now, it has been largely an artisanal profession, investment casting. There's a lot of knowledge that inherited knowledge and subjective knowledge and maybe decades-long direct experience relating slurry properties to the quality of the shell and the quality of the final product. So we're in the midst of a transition ourselves from being simply a sensors company to a vehicle for transmitting the artisan's subjective experience of slurry consistency into a form that can be taught to the younger generation. And another just brief comment is that I realized that I grew up in an analog world. So when we look at how slurry characteristics are measured nowadays, it's largely by an analog process. And I'll get to that in a moment, but this is the agenda for the talk. So we're going to review some of the current methods for measuring slurry characteristics, and then we're going to move on to the motivation for improvement of measurement systems. What do we mean by improvement? Is it simply shifting to a sensor, or is it improving the overall process? And then we'll talk a bit about something that some of you may be familiar with, which was the last improvement that we made was self-cleaning sensors, because as some of you may know, slurry tends to stick to sensors, and we saw that as a primary challenge of how to clean up the sensor in situ. Then we'll move on to our latest developments, which involve smart filtering technology, which to improve not only the accuracy but the operator's confidence in the measurements. Like how, if you're operating a slurry tank and you see a change in the indicated viscosity, does that call for action or not? And if it's not clear, this can lead to unnecessary dilutions and so forth. So we'll briefly look at smart filter implementation and finally the outlook for these processes. So first, let's take a look at how slurry characteristics are currently measured. And again, this is something, well, first of all, why slurry consistency is important. Slurry has to stick to the pattern, and it's got to make a reproducible layer on the pattern when the pattern is pulled out of the slurry, which means that that's influenced by both viscosity and density of the material. The higher the viscosity, the slower it's going to drip off. the higher the density, the faster it's going to drip off. So the combination of viscosity and density are both crucial to shell thickness. Then there's also the questions about the binder stability. Like what's happening in that tank? Is the colloidal silica binder beginning to gel? How can we detect that and correct for it before things get out of hand? So these are the current options for measuring slurry properties. You have efflux cups that where you just time how fast the slurry drains out of a cup with a certain volume and a certain opening size. And for measuring density, you have in the middle there, you have like a standardized container that has a certain volume of slurry in it. You know how much the container weighs, and then you weigh it it's full of slurry, and you can calculate the density from that. Then for those are a few different kinds of cups there, and then you also see a Brookfield style viscometer. It's a laboratory instrument, and a hydrometer. And the last one is you have a standardized plate, you dip it in the slurry, you measure its weight afterwards, and that's the plate weight. It's how much solids material is being left behind. So another option, which has become more popular, is the continuous in-tank viscosity and density measurement. And there you do away with all of the manual point measurements that require sampling of the material, and you measure it in situ as the tank is being mixed, and so presumably this will better represent the condition of the slurry as it's being used. So what are some of the problems with existing methods? I mean, aside from the intermittent nature of cup measurements, for instance, the interoperator reliability is not so great. There have been some studies done, and it's been found that experienced operators can get very consistent and confident producing results, but others get more random results doing measurements in the same slurry at different times. Also, they're all intermittent operations. They have to be done at a certain interval. Whether they actually get done depends again on the operator. And they're time-consuming and messy. You've got to clean that cup, and you have to be sure that the aperture on the cup is really the size that it was meant to be. Otherwise, again, you get distorted readings. But despite that, there are some advantages to traditional methods. And in the world of manual operations and analog viewpoint, let's say, you could look at these manual methods as the operator's instruments. They're instruments that the operator knows. They know how to produce good shells given the limits of these methods, but they can rely on them. And the fact that they can produce good shells despite the so-called primitive nature of these methods means that they have a great deal of value. So when we present a new method for measuring viscosity and density, they had better measure up to the old methods. We can't just invent a whole new system and expect that that's going to be addressing the operator's needs. So what's the motivation for improving these systems? What are the advantages and limitations of in-tank slurry measurements? So as we said, of course, you get continuous measurements, and they produce digital outputs that are compatible with enterprise data systems, and all operators get about the same results with them. But the limitations are the slurry itself. I mean, slurry is built to stick. If it's going to stick to wax, which has a relatively low surface energy, it's going to stick like crazy to metal parts. So now it depends, of course, on the slurry, but many operators have found that you have to do very frequent cleanings of these things to make the measurements reliable, and we'll get onto that in a few minutes. Another, let's say, hindrance to acceptance is that there's no clear and universal correspondence between cup seconds and centipoise, which is a more quantitative or scientific measure of viscosity. And being a sensors company, primarily our sensors read in centipoise. So operator confidence depends on being able to make reliable correspondences between their traditional methods that they're accustomed to and the types of measurements that our instruments produce. And then there's the problem of cleaning schedules. So you have to somehow coordinate cleaning of the sensor with the other operations in the shell room, and that can get a bit complex because then these intervals are not always clearly defined. One method that some of our clients have used is they have a robot arm that picks up the sensor out of the tank and puts it in a bucket of water, maybe swishes it around a bit, pulls it out and puts it back in the tank. And that works well, except it's extra equipment and it's one more thing to attend to. Maybe the biggest hindrance, I'm speaking German, this is terrible. One of the biggest difficulties is that the data may be noisy in ways that are more difficult to interpret. And I'll show that later in the talk with some actual data. And George Solomon from Nalco will be going into that in greater detail at 4:30 today. So here's what happens typically. If you put one of our sensors in a slurry tank without attending to the cleaning or anything like that, in this case, over a time of several days, a deposit can build up on the sensor. And now our sensors operate by having there's a very tiny vibration that goes on in the tip of the sensor. And by measuring the characteristics of that vibration, that gives us information about the slurry properties. But if you get solids depositing on that resonator, this tip of the sensor, it distorts the readings. So this is a typical viscosity trace that an operator might see over the course of several days. Like at a certain point, deposits begin to form, and the apparent viscosity rises and at the same time gets noisier. So what happens if the viscosity rises? So the operator says, oh, we've got evaporation. Like this is something that will typically happen over the weekend, for instance. And the operator says, oh, the viscosity is rising, we have to dilute the slurry. But the viscosity hasn't been rising. There's been deposits forming on the sensor, which means that if you dilute at that point, you have an over-diluted slurry tank and you've got other problems to solve. So this is one of the prime factors that motivated our next development. So the next development, which some of you, I think this was also presented last year, so is self-cleaning CleanWave technology. So have you ever seen a wet dog trying to dry itself off? You know how dogs go? They do this little dance with the body and water flies off the dog. So this was kind of the inspiration for CleanWave technology. So that's a sensor that's had a hard time in its life. It's full of deposits and gunk. So you start on the left, you see our SRD sensor. This is our viscosity and density sensor. That's the little tip there that is vibrating at high frequencies. And we added, in the second picture there, we added this little lump on the side of the stem, and that contains a pneumatically actuated vibrator. And what that does is it shakes the dickens out of the tip of the sensor. The whole thing vibrates, but at a much lower frequency than the frequency of the actual measurement vibration. So the result is that you can actually leave that vibrator running while the sensor is making measurements, and I'll show you in a moment what the consequences of that are. So in the last picture there, you see the SlurrySense, the sensor, the probe with its attached pneumatic vibrator on the tank mount adapter. So it can be mounted on the side of a slurry tank. So what happens here? So we have a little model slurry tank. I don't know if you want to know about our model slurry tank that's only 7 liters but simulates a big one, talk to me after the talk. So we have our model slurry tank, we have different slurries, and we know that some of them are much noisier than others. There are some you can put the thing in, it stays clean, it's no problem. Others are full of little particles and stuff, and they get... So what happens is almost immediately after you put the sensor into the noisy slurry, you get what looks like random readings out of it. And then you turn on the vibration, and wow, look what happens. Suddenly the trace evens out, and it's almost horizontal. It's horizontal, basically. It stays that way until you turn the vibration off, and then it becomes random again. Now, the interesting thing is that if you compare the two periods where it's random, there's not much correlation between those two. So if you're trying to pull data from the sensor without the vibration turned on, you're not going to get anything that's confidence-inspiring. On the other hand, after another hour or so, what is that, about another 30 minutes, you turn the vibrator on again, so it's had 30 minutes of being in this rotating model slurry tank, and almost immediately it jumps back to the former level where it was before we turned off the vibration. And this is true of both the viscosity and the density. So this is the first level of cleaning up the trace so that it becomes intelligible to somebody who's accustomed to cup measurements, for instance. So then, well, let me go back one thing here. Now, to us as sensor makers, we think, wow, that's incredible, look what it does. However, if you give it to somebody who has to make decisions based on the output of the sensor, when you look at these, there's still noise there. There are still things that are going up and down. Which one do I choose? And to a certain extent, people will develop a sense of what the constant portion of that is, but a slurry tank operator should not have to be a measurement engineer. They should be doing the best shells that they can possibly do. So let's take a look at what you can do about that residual noise to raise the confidence level in the measurements. Whoops, wrong button. That doesn't raise confidence. Let's see. So the advantages of self-cleaning, continuous. There's no need to interrupt the operating cycle of the tank, and surface remains free of deposits. The limitation is that not all noise is caused by deposition. You can have, for instance, little chunks of residual shell material floating around in the tank or rotating around in the tank that will cause rapid fluctuations of the reading. You could have impact with the sensor element, for instance. Variable flow velocity can also create local variations in the readings, and so in other words, our sensor might be a bit too sensitive and too quick to respond to really reflect the bulk properties of the slurry, and the bulk properties are what ultimately the caster is interested in. And finally, like you could have external noise sources like electrical transients from heavy machinery in the neighborhood, and that would give unpredictable noise. So you think to yourself, okay, if I'm a measurements engineer, let's say, and I see a noisy signal, I think, let's put an average value filter on it. Let's just put it through a slow, like a low-pass filter, and take the mean value. Unfortunately, well, we tried that, of course, and it doesn't work very well. And the reason is that I'm going to go skip over these. Get to the meat and potatoes here. Here's a situation where you have a trace of the output of our sensor. So you see the viscosity measurements are bouncing around a bit, and then they gradually rise, and the operator dilutes the slurry. And sure enough, the value falls. And that happens on repeated dilution events, so an operator can learn to filter that with their eye. They can say, okay, this looks like rising viscosity. Yes, this was over the weekend. The tank was rotating. It's been hot in the plant. Seems reasonable to dilute it there. But so if we try to apply a low-pass filter to this, it doesn't work very well because a lot of the excursions are in one direction. Like if the primary source of noise, for instance, is that you're getting bombardment of the sensor by little particles of residual shell in the fluid, then they're all going to be in one direction. And what they're going to, like, the squeaky wheel that needs the oil, they're going to have they're going to be overemphasized in a simple low pass or mean filter process. So let's take a look at what we can do with smart filtering. So just a word about smart filtering before we get to the data. Let's say I have a slurry tank that's got 100 or 1,000 liters of slurry in it. And I take a cup with a liter of water and dump it into that tank. And the tank is mixing, it's rotating. How long do you think it's going to take before you get a uniform mixture of that 1 liter into the tank? It's going to take a while. It's going to take at least several minutes to really impact to make a tiny difference in the viscosity of that slurry. So if you've got a slow, if you have a slow rise in viscosity due to evaporation, for instance, because you've got a hot climate in your room, then the noise that you see, if you're an experienced operator, you know that noise cannot be happening because the slurry properties are changing that fast. Now, they could be changing locally very fast around the sensor, but that's not what's important. You get this big pattern tree dipped into this thing. It doesn't care about the micro variations in the density and viscosity in the neighborhood of your sensor. So a smart sensor or a smart filter, what it's got to do is it has to somehow emulate the eye of the operator and the knowledge of the operator. And the operator knows that whatever that sensor is putting out, if it's got variations that are going over the course of a minute or two, they cannot be relevant to the actual bulk properties of the material. So the challenge for a smart filter is to produce a filter algorithm that's capable of recognizing long-term trends and tailoring that to the properties of the process. So for instance, if you know that I'm going to use the term time constant. If you know that you throw a bunch of water in your tank and you get a response over a certain length of time, I'm going to call that something like the time constant of your tank. And if you have variations in the sensor output that are much faster than that, you know automatically that they're not relevant. So a smart filter will know something in advance, like the operator will know in advance what the properties, the time properties of the slurry tank are, and will compensate for that without being overly influenced by outliers. So for instance, in this trace here, we see the pink, the magenta trace is raw data coming out of an SRD. This is over the course of minutes. And there's the first interval is biased toward negative values. They're outliers. Whatever their source, they're going down more than up. So you want to be careful that that's not then, a mean value would be underestimating the density because it would be pulled down by those outliers. The second interval there, that's where you've got the vibration turned on. And the interesting thing is there that it's a bit more symmetrical, but still there are these outliers that can always influence the bias. They can bias the output. The blue trace is a filter that takes into account the time constant of the slurry tank, plus it removes the outliers that can bias the bulk properties. So what you're seeing with the blue line is something that gives a much more, let's say, a fairer estimate of the bulk properties of the slurry that are actually relevant to the casting process. Now, those may look like big excursions, but you see that the vertical axis there, that's like 0.01 grams per cc or kilograms per liter of density. So that's pretty constant, pretty clean data. So here's another example of that. This is our density measurement. That's our viscosity measurement up there. And in viscosity, you see that the outliers, the positive outliers, tend to outweigh there are fewer negative outliers than there are positive outliers. So without our smart filtering algorithm, that would pull the viscosity upward unfairly, because if you look at it objectively or without that blue line, I wish I had a thing where I could turn off the blue trace and you could estimate that. You can see that the blue line ignores the outliers. So this is one of the central functions. So two functions of a smart filter. One is it shouldn't be distracted by irrelevant data, and its time constant should reflect the realistic physical time constant of the slurry tank. And here we're moving closer to something that mirrors the experience of the experienced operator. So I think we dealt with this already. Yeah, this is just a recap of what I mentioned. It looks at the values with an experienced operator's eye. I think that's the most important thing. And to do that requires consulting with experienced operators. I think in the area of knowledge transfer, I think this is one of the central things. And that was certainly one of the things that reoriented our own attitude toward our measuring systems, because it helped us to realize that we were trying to solve a real problem without full knowledge of what was required for that. So it required dynamic interactions with many shell room operators from whom we had to learn. We started out thinking they had to learn from us how to use our sensor to better their operations. We wound up learning at least as much from them as we expected them to learn from us. And I think that this is, if we forget this, it's very easy to revert to the idea hey guys, we're giving you a new tool. It's bright and shiny, and you just got to learn how to use it. Partially true. We have to learn from experienced people and not try to behave as though we're investment casting experts. We're sensors experts. So what's the outlook for this? So CleanWave, sort of a recap. So, requirements fulfilled. Okay, here we go. So the CleanWave technology minimizes data variability due to deposition. So we're taking one source of variability out by nipping it in the bud, by attacking it at its source. Then once we do that, then the resultant measurements show latent variability due to phenomena that don't have much to do with the slurry tank. So the initial smart filtering trials are showing us the potential for eliminating irrelevant noise and variability. So this is a positive reinforcement for going further with the smart filtering idea. And ultimately, we, of course, want to make this filter as smart as possible. And that's our assignment for the coming year. And hopefully by next year, we'll be able to show you, add one more point to this. So is that it? The outlook, automatics. Oh yeah, one more point. We've just been talking about human operators adjusting slurry tanks. Of course, one of the goals of all of this is to provide totally automatic control over slurry consistency. So in order to do that, you need relatively clean data. If you supply a control system with data that's got a lot of ups and downs in it, it's going to create trouble. It's going to try to make corrections where no corrections are due, and it's going to neglect making corrections where they are due. So the two things have to work together. In other words, now you have, in essence, you have three components. You have the operator's experience, you have the control system that you want to take over the least creative task from the operators, and you have the measurement system. And the three of those have to cooperate on defining what is proper operation of a slurry tank and how that's reflected in the sensor output in order to design the proper smart filter. And that could change. It could be that for one type of slurry you need one sort of filter, for another type of slurry you need another sort of filter, or you need a filter that can actually detect what slurry is in that tank and make the appropriate corrections. And I think from the human standpoint, continuous improvement relies on feedback from experienced shell room experts. I think that's the biggest channel that we need to keep open, and in a way it's the most challenging because to have somebody take the trouble to install the sensor in their tank is not trivial. They have to interrupt operations perhaps. So, but a lot of people have tried it, and a lot of people have been interested enough in it to share their data with us, and that's been very helpful in moving this whole project forward. So that's it. That's basically what we have to offer today, and I'm happy to answer any questions that might come up around that.
Thanks a lot,
sure,
Joe. And of course, we see now if there are questions in the audience. I did not want to stop you, so
no, that's
we were
that's good.
running a little bit long in time.
Yeah, sorry about that. Yeah.
But I see there are some questions already coming.
Yes, thank you for your presentation. Very interesting. I've got actually two short questions. I'm right here.
I can't see a thing.
I'm here. I'll wave.
Okay. Yeah.
Your research results incorporate a pretty low density backup slurry of about 1.5, 1.6 gram per milliliters. What results did you achieve with a much heavier prime slurry of about 3 grams per milliliter?
I haven't been directly involved in these tests, but Sunil or Daniel, maybe you could say something to that.
Sure. So basically, the SRD density platform that goes up to 4 grams per piece. So drilling mud and stuff like that. So in terms of, So in terms of basically the same measurement, the higher densities, we have not seen any big issues, like typically the work. It's slightly harder to deal with them in our own labs, so that's why the data you see from us, which we can share, tends to have like the lower densities at 1.5 and stuff, but the customers have been working with much higher densities.
How does the system work with fiber-enhanced slurries? You see the fiber here against the...
So I think we have seen that actually causes the noise oftentimes in the slurries. So part of the thing that we did with the CleanWaves and the smart filtering will avoid that noise. And we will then be able to like give a much cleaner signal, the control signal, as we may call, to basically have automated dosing systems.
Thanks a lot. Any other questions in the audience?
Hi.
Yeah. Thank you for the presentation. Just
Sure.
a quick question. So with this system, would it be possible to measure in different points of the tank the
Yes.
slurry capacity, and would it be better maybe to monitor at different layers?
Yes.
Yeah.
Yes. Because the question came up in an earlier presentation a couple of years ago. Somebody said that sensor is no good because when you put it in different levels, it doesn't, it gives different values. And another person who's been using the sensor said, that's your mixing process. Your mixing process isn't working properly, and that stratification is real. So yes. Am I answering your question? Or?
Yeah.
Okay.
Thank you.
Sure.
Now, sorry, Joe, I apologize, but I have to stop the questions. But for any other questions, you can find Joe at the booth.
Yeah, well, I'll
Rheonics.
be at the booth, and we can talk further.
And thanks once again, thanks.
You're welcome.